Welcome everyone, and importantly, let me welcome Professor Nicolas Brunner from the University of Geneva. So I guess I don't really need to introduce Nicolas too much, right? He has contributed, significantly to many different topics of quantum information, right? Namely in quantum crypto, foundations of quantum theory, as well as more, recently, I guess, in the past 5 to 6 years, also in quantum thermodynamics. So without further ado, I would hand over the stage to Nicolas Brunner, who would speak and talk about experimental relativistic zero knowledge proofs, which was recently published in Nature last year. Okay, Nicolas, over to you. Good luck.
Okay, great, thank you. So good morning, or maybe good afternoon, I should say. So yeah, thanks Charles and Guy for the invitation. It's always a pleasure to be at CQT, even though only sort of virtually. Yes, so today I'll tell you about this recent work on experimental relativistic zero knowledge proofs. So that was a nice collaboration we had over the last couple of years with the group of Claude Crépeau at McGill in Montreal, and in Geneva between the groups of Hugo Zbinden and my own group. And so I would say it's quite a sort of unusual project, at least from my point of view, because it has almost nothing quantum in it. Okay, you will see some entanglement on the last slide, but apart from that, it's just computer science and fast electronics. And okay, here I should make probably a little disclaimer, because I'm an expert neither of computer science nor of fast electronics, but okay, I'll do my best to tell you a bit what is the story behind this work and okay, why we think it's actually quite interesting. Yeah, I should also say that there was, so our paper got published last year in Nature, and there was a very beautiful News and Views article by Gilles Brasseur, from which I also got some inspiration for today's talk, actually. All right, so let me start maybe this talk about a very basic introduction to zero knowledge. And in fact, I will tell you a little story here about Sébastien Dessignol, who was my PhD student until last year, who was also leading this project, actually. And so Sébastien defended his PhD in the fall. Okay, so Sébastien defended his PhD in the fall and, decided to, after that, go on a long trip to the Middle East. And it's really, trip by land, right? So he went through every place in the middle. And of course, in a trip like this, right, you end up sometimes in very remote places. And then comes the question on how you withdraw money, right? Because you need some cash in order to for your subsistence. So you could imagine Sébastien arriving in a place like this. And, okay, and then it's a dilemma, right? Because you have your bank card. Are you going to put your bank card in this device, which has all your bank account number, etc.? Even worse, are you going to dare to input your secret PIN number, right, to get the cash? Because of course, you never know. It could well be that this is just a hoax and that some bunch of criminals will just get your data out of it, right? But okay, ultimately you need the cash, right? And you need to eat, and so most probably you are going to give away, all the secret data. And okay, most cases this is fine, but in some cases it goes wrong, right? As we all know. In fact, without needing to go so far into the wild as Sébastien, even in Switzerland a couple of years ago, there was a big affair where, some actual ATMs were sort of modified by criminals, and they would put a little device that would just scan your card inside. At the same time, they had a very small pin size camera that would check what is your PIN number, and then for some people it was dramatic because the next day their bank account was just empty, right? Okay, so that's a sort of general problem, right? So it's a problem about authentication, right? And so here the problem comes from the fact that in order to identify oneself, one, usually reveals one own secret, right? So of course it would be much nicer and much safer if there would be a way to identify without revealing one's secret, okay? But naively you can think, okay, how can the bank check that I'm me if I don't reveal any secret, right? So surprisingly, perhaps this is actually possible. And this is something known as zero-knowledge proofs that were invented in computer science already back in the 80s. And formally, it's the following idea that you have two parties, a prover and a verifier, right? So the prover would be the client of the bank, and the verifier is the bank. And so the prover would like to convince the verifier of the validity of a certain statement without giving away any information about the proof, right? So in a sense, that would mean that you are the client, you go to the ATM, you can prove to the bank that it's you, right? Without beyond any reasonable doubt. And yet the bank has no idea what is your secret PIN number, right? So it's actually wonderful, right? Because even if you think of a more dramatic scenario where some hackers, get into the servers of the bank, and typically as it's done now, if this happens, they know everything, right? The bank account numbers, the secret codes, they know everything about the clients. But if you would have a zero-knowledge architecture, you would be safe against this, right? Because at no point the bank knows the secret of the client, right? Okay, so early on, of course, this already attracted attention. And maybe just to give you a sort of first intuition on how something like this can go. Maybe let me just give you, before that, what are the key properties that we would like, right, for a zero-knowledge scheme. So there are three things we want. First, the scheme should be complete, in the sense that an honest prover can convince the verifier, right? If you go with your card to the ATM and you can never get cash back, it's of course useless. Then it should be sound. If someone dishonest tries to pretend to be the prover, right, they should never be able to pass the test and get the money. And finally, should be zero knowledge, right, in the sense that after the process, after the authentication is done, the verifier didn't gain any information at all about the secret, right? That are the three things we want. So let me give you a very naive example of how something like this can work. So you imagine you have a friend who pretends that they can, perfectly distinguish between, say, two famous soft drinks, right? So how can you verify this? Well, you take a glass, you choose either of the two drinks, you hand it to your friend, can even, close his eyes so that he doesn't see the color. And then the person will take a sip and tell you which one it is. And if you repeat this 200 times and he gets it right every time, okay, you are convinced, right? He can perfectly distinguish. Of course, during that demonstration, you gain no information about how he does it, right? You wouldn't be able to do it yourself. Okay, so that's a sort of zero-knowledge proof in a sense. Now, if we want to make it a bit more formal, and nice properties of these ideas actually is that they are sort of universal. So what people showed already a long time ago is that for any statement for which you have a standard proof, you can also do it in a zero-knowledge way. Okay, and hopefully that should get a bit clearer in the next slide. And so if you think about what sort of problems would be good for implementing a zero-knowledge, right, you quickly arrive at the conclusion that this should be a problem in NP. Okay, so why is that? Because, okay, of course, you want a problem that is hard to solve, right? Otherwise, I mean, everyone can go and the verifier eavesdropper, they all know the solution. So it should be hard to solve, but it should be easy to verify, right? So these are problems in NP. And so an instance of such a problem is tree coloring. So what is that? You have a graph given to you, so a structure with a number of nodes and a number of edges connecting them. And then you say that a graph is tree colorable whenever it's possible to attribute one color out of three, right, to every node, such that every pair of nodes connected by an edge have different colors, right? So here you see, for instance, 1 and 2, they are connected, they are different colors. 1 and 3, they are the same color, but they are not connected by an edge, right? So that's fine. All right. Okay, again, back in the 90s, people already came up with zero-knowledge schemes for tree coloring, which is, in fact, very nice because tree coloring is not only NP, it's NP complete. So it's sort of universal, right? So in that sense, right, if you have a zero-knowledge scheme for NP complete problem, then you see that you have it for all problems in NP, okay? So that's in a sense, I should give you the intuition why it's so general then. All right, so how does it usually work, right? So what were people thinking back in the 90s? Well, they were thinking, let's say, of what we would call a standard zero-knowledge proof. This is the situation where you have one prover, one verifier, right? One person going to the bank and cash machine, for instance. So this is possible to implement such a schemes. However, it relies on some extra assumption, right? When I say extra assumption, I mean beyond the hardness of the problem used itself for the scheme. And this extra assumption is related to some sort of coding of the answers, if you want, right? So the way the standard zero-knowledge proofs works is that the verifier asks questions, the prover answers, but of course the answers are encoded in some way such that the prover, the verifier gets no information about the proof. Yet he can still verify that some statements are correct. And so, for instance, to do this, to encrypt, you would use maybe something like RSA, right? So there is a computational assumption here that the encryption part is solid, right? So, for instance, you may rely on a one-way function, right? However, this creates a risk because ultimately it might be that this breaks down, right? For instance, might be that the function that you used which you thought was a one-way function turns out not to be a one-way function in the end. And okay, then the zero-knowledge property is gone, right? And so if you want to implement these kind of ideas with the perspective of a long-term security, this is not so nice, right? So it would be very nice to get rid of this computational assumption. And I should add, it's very strongly believed that it's impossible to do this standard zero-knowledge without this extra assumption. However, there is a solution, which people also invented already a long time ago, which is to go to a so-called multi-prover scheme. Okay, so now the idea is that you have not only one client, but you have maybe the client and an agent of the client, and they are going to some bank and maybe another shop of the same bank in a different place. So why does it help? What's the idea? Well, you can think of the situation when the police arrests a group of criminals, right? Suspected criminals. So what do they typically do? They bring them back to the police office. They put them in separate rooms and interrogate them separately, right? And during that phase, of course, the criminals cannot communicate, right? So they have to come up with their own version of the story. And ultimately, if this was all fake, well, then the police will see some inconsistencies in their declarations, and then they are trapped, right? So here it's really the same idea that you want the provers to be separated, not allowed to communicate, and then the verifiers can make this interrogation, okay? And here comes in the first bit of physics, I guess. So how do you prove that some provers cannot communicate. You see, because unlike the criminals in the police office, I mean, the provers could use some quite sophisticated technology and so on. But here you use just the principle of relativity, right? So you make this interrogation happen in a space-like separated regime, and then you know that you have security, okay? And so here it's nice because you could replace a computational assumption with a physics assumption, right, for the security. So it's very much like what we usually do in QKD, right, where you go from private key, public key schemes to QKD, right? So now security is based on physics. Here it's a bit the same idea, except that it's not the same physics, right? It's relativity instead of quantum mechanics. All right, so let me now show you how a protocol works, or what's the general idea. I will start with a simplified version, then you get the idea. Here is the sort of photo already of the experiment. So this is a photo from our previous building where, in fact, this experiment was done in Geneva. I will come back to that a bit later. So what's important now is that on one end, you have one pair of verifier and prover, right? And they interact locally here. And at a distant place, you have a second verifier and a second prover, right? Okay, so now it goes like this, right? So the challenge is to demonstrate that the provers know a three coloring of a given graph. Okay, so imagine again the client and the bank. So when you start your relation with the bank, you define a graph that is your client number, if you want, right? That is a graph. That's just the structure of the graph, the nodes and the edges. Okay, and the secret of the client, the secret pin, this is the three coloring. Okay, so when the client goes to the bank, okay, the bank brings forward the graph, and then one would like to verify that the client knows indeed the three coloring. Okay. Okay, so then you proceed like this, right? The verifiers will choose randomly in advance a certain number of pairs of vertices that are connected by an edge, right? So let me call them I and J. And then the first verifier will ask the color of the vertex I to his prover, right? While verifier 2 will ask the color of the other vertex to the other prover, right? And because, of course, the point is that the provers do not have the time to communicate, right? To know which pair of vertices they were asked, right? It's done locally. Okay, if they actually don't know the three coloring, it's very difficult to pass such a test, right? Almost impossible, actually. But if you know the three coloring, then you just need to look up and answer, right? All right, okay, so you would repeat this test a large number of times, and the verifiers can compare the answers, and if the colors are always different, okay, then they know that it's very likely that the provers are indeed the right ones. Okay, so as I said, the provers announce their colors. There is one point, of course, where you should be careful is that if you look at it like this, it seems like the verifiers still learn about the colors of some vertices, right? So it's strictly speaking, it's not zero knowledge. But here there is an easy trick, is that you constantly reshuffle the color code, right? So in every round, you invert the colors randomly. There are different ways to do it, right? And so therefore, the prover, the verifiers get no information about the color, because in every round the color is just different, right? So this is very nice. It's complete, right? Because honest provers will pass the test. Dishonest provers have a vanishingly small probability to pass it, right? Now, the verifiers learn nothing about the three coloring. Even with this color reshuffling, this is actually not quite true. So here, the point is that this scheme would not be zero knowledge. And that's because of the following reason. So imagine that the verifiers would be a bit more tricky. And what they would do is that they would ask for a pair of vertices that are not connected by an edge. Okay. In that case, it might be that they learn that these two vertices are of the same color, right? And that is an information that will help them a lot to find the three coloring. Okay. So that's why this kind of scheme is not zero knowledge. Okay, but there is a sort of fix to it. You can modify a little bit, but with the same spirit to make it really zero knowledge. And so this brings me to the actual protocol. So the one we implemented is a simplified version of one that was presented in this paper here by Claude and colleagues in 2020. Okay, so here is how it goes. So our provers have some random or constantly reshuffled three coloring, right? Which I write CK here for each vertex k. CK is a trait, right? That gives the color. And then they have a sort of, they use shared randomness, right? On top of that. And then this shared randomness is used to have a sort of bipartite decomposition of each color, right? So they have pre-agreed traits LK0, LK1, right? Such that you see the sum mod 3 of LK0, LK1 is equal to CK, okay? Right? Good. Now, so how does it work? Okay, so the verification goes like this now. So you see each, so verifier 1 asks for an edge ij, okay, and some additional bit value b, okay? And v2 will ask for some I prime, j prime, b prime, okay? Now here's how you do the first part of the verification, is that both v1 and v2, you see they choose the same edge, okay, I and j, I and j. But one of them chooses b equals 0 and the other one chooses b equal 1, okay? And so therefore they learn LK0, LK, well, LI0, LI1, they can construct CI, and LJ0, LJ1, and they can construct CJ, right? And then they can check again that the colors are different. But because the color code is reshuffled, they also learn nothing, right? Okay, good. Now, the good thing here is that if the verifiers would now ask about two vertices not connected by an edge, then the provers are not going to answer, right? All right, there is an additional thing though to make sure that this thing works properly, is that sometimes the verifiers should actually pick different edges with a common node. Okay, so let's say, for instance, that I is equal to I prime, but j is different from j prime. And in that case, they will take the same bit value. So set b equal b prime. Okay, so in this sense, you see, this will allow the verifiers to check, right, that this decomposition here of the color is indeed, that it really corresponds to a three coloring, right? That the provers are not cheating, okay? Because then they can check that, for instance, this Li0 here is indeed the same on either side, okay? All right, that's it. So you see, this is the protocol. So why is it a good one for a practical implementation? Well, it's because you see the amount of information in every round is very small, right? It's just two colors, basically. The calculations also that the provers have to do are relatively easy. And another thing that's important, which I didn't put here, but is that the number of rounds to verify soundness, okay, up to some predetermined security factor is actually also, it also scales pretty good, as you will see in a minute. All right, so let me tell you now about the experiments. So, of course, the main challenge in such an experiment is to minimize the distance between these two pairs of prover verifiers while still ensuring the space-like separation, okay? And so the distance is essentially constrained by two things. First, there is the latency in the answers, right? Because the verifiers choose a question, they communicate it, and then they get the answer back, right? But of course, the prover need to calculate something, send it back. So in practice, this is not instantaneous. And then, of course, there is the precision for the synchronization of the verifiers, right? Because verifiers must ensure the space-like separation. Okay, so to do this, the good sort of devices are so-called FPGAs, right? So what are FPGAs? They are sort of, let's say, mini computers, I would say, that are programmable. So they can do, they are not as universal as a computer because they can do only relatively simple types of operations. But they have two advantages: that you can program them in a very easy way, right? They are reprogrammable, and then they are fast, okay? And they have this way to connect to them that is also done efficiently and so on. And these are devices that are typically used in Hugo's lab for quantum optics, right? So in quantum optics, where you need to synchronize things between photons coming from different sources. So for this, you need very fast logic, and that's why FPGAs are very good for this. So in practice, it looks a bit like this. So you recognize a sort of PC board, right, that you can put inside your computer, and the FPGA would sit here, right? So it's this little chip here, and so then you can access it via some computer program and connect it as you wish, and you see then it's connected to different pieces here, and you can also connect two of these FPGA via some optical links and so on, right? And just to give you an idea, this sort of setup that we used in our experiment, it costs about $100, I think. Okay, so it's not super expensive stuff. Okay, so we did two experiments, one sort of long distance. So here the idea was to do the synchronization via GPS, right, which is quite convenient. And then you see, so what we have on either side is that the verifier has an FPGA, right? There is a fiber optical link to the prover, right? That also has an FPGA, same thing on the other side. And then in order to ensure the space-like separation here, we needed 300 meters. And this is basically coming from the, the precision of the GPS, right? Which is good, but limited. And then we also went for a shorter distance experiment where we could improve on the synchronization. And here it's done via direct communication from verifier 1 to verifier 2. Okay, so there is, again, an optical fiber here going, so sending a signal that, tells when the question was sent to verifier 1. Okay. And so here we could implement it on a distance of about 60 meters, okay? So here is how our experiment looks like. Charles, you recognize the premises, I guess. So let me come back to the sky photo. Okay, so here it is, right? So this is our old building, which is in the outskirts of Geneva. You see it's surrounded by fields and so on. And there is this very sort of long parking place here in the front, about 60 meters. And so on a nice, well, I was about to say sunny, but it was not so sunny, but at least not raining day, right? a dry day, well, we put outside the equipment. Here you see it's a very field type experiment, of course. With just a computer. Here you can see the FPGA. Okay, I wouldn't be able to tell you if this is the verifier or the prover, but okay. So this is one end, right? And at the other end, okay, here you see the same sort of setting. You see the other table is there in the back. Okay, and that was how the experiment was done on short distance. Here is for the long distance experiment. Here is the same building as before, right? So you see the nice fields here and also nice houses with swimming pools. And so for the other side, we went to another building of the university campus, which hosted the canteen. We used to go every day to have lunch. So you need about 5-10 minutes to walk from here to there, right? Okay, so that gives you an idea. So now, what is the main point? Well, of course, it's one of them is the synchronization of the verifiers. So if you do with GPS, you see the precision of the GPS is about 150 nanoseconds. And there is also, of course, an internal precision of the clock inside the FPGA, right? And so in the GPS version, the imprecision is about, okay, of this order, right? So 200 nanoseconds, that's the lag from the synchronization. While, of course, in the triggered version, there is essentially no loss of accuracy in the channel, right? Because this is very precise. So it's just the internal lag of the FPGA. And then, okay, so what about the latency of the answers? So of course, the point is that each time the prover receives a question, need to look up the color of a vertex, right? And okay, also reshuffle the color code, do this decomposition and so on with randomness. And so this takes a while. By the way, if you want to know the random treats were actually generated quantum mechanically, right? Using a ID Quantique device. This is the only quantum part of that experiment, so maybe I mention it. And then, of course, there is also latency because the optical devices that generate the communication. So all that has a bit of lag. But in total, the time needed once you send a question to get the answer back is about 160 nanoseconds. And so what sort of parameters did we use? Well, we used a pretty large graph, about 500 vertices and 1,000 edges. Okay, perhaps I should tell you how we generate this graph, but okay, maybe I can leave it later for a question if there is time. So as we said before, right, the time for one round is about 200 nanoseconds for the short distance experiment. And so in order to get, to find out how many rounds we should do in order to improve reasonable soundness, right? Well, we would like to have a security parameter, which is about 100, right? Which means that a dishonest prover would have a probability to pass the test with probability at most exponential e to the minus 100, right? So that's quite small. And so to have that, we needed 500,000 rounds. And given the time of one round, the total thing is done in 1 second. Okay, so it's not too bad, right? Of course, when you want to go to the cash machine, you don't want to wait for 10 years that the authentication is done. But okay, 1 second is very good. Okay, what is perhaps not very good yet is the distance, right? Because 60 meters, okay, you can imagine it for some applications maybe, but if you think of a cash machine, this is not so convenient. But of course, as I said, the equipment that we used is very low-tech somehow, right? That was also the point for experiment. Also because we didn't have more expensive ones. But if you would go to a, state-of-the-art FPGA that costs maybe $10,000 or something like this, Everything is much faster, of course, and there we estimated that you could implement this thing in a room, right, on a distance of 6 meters, so reduced by a factor 10. And if you wanted to go down even further, maybe reaching the 1 meter scale, that might be possible, but there you need some integrated chips, right? So this is the so-called ASIC technology, but this is something quite standard, right? In mobile phones, for instance, you have such chips, and they are integrated. They are they are meant to work for specific tasks. Okay, they are not programmable, so they are dedicated. So that's why they can achieve specific tasks extremely fast, right? Much faster than FPGAs. The problem with that, so why didn't we do it, is because to create the matrix of this ASIC, you need a couple of million, right? Then the next ones you can do very cheap. So if you're a big phone company, it's fine, but for us, it's a no-go. All right, so these are the perspectives for improving the current realization of the scheme. And so what could you imagine doing with this? Well, you could imagine having, if you can do it on 1 meter, you could imagine this sort of double terminal ATM, right? So as a client, you would come with your 2 cards that you insert in 2 terminals separated by 1 meter. Then the verification goes on, and if you pass, then you get your cash. Okay, so that's quite nice indeed, but I don't know how realistic it is. If you think about how many ATMs there are around the world, changing all of them to double terminals schemes, that doesn't sound so good. But on the other hand, there are other applications that use zero knowledge, in particular in blockchain architectures. There are some cryptocurrencies that use zero knowledge. Okay, so like the standard version of zero knowledge, right? But you could also imagine other applications where maybe having this improvement on the security of the authentication might be very useful. Okay, so for that we'll see in the future how it goes. There is another point where progress is also needed. Is what about imagining now that the provers are quantum, okay? Because so far, what we said in our protocol, security is proven, right? Soundness is proven with the soundness value that are indicated before, but this is against classically correlated provers, right? So of course, you can imagine now whether entangled provers could do better, right? So for the present protocol, we actually don't know, okay? But there are ways actually to make it work, at least in principle, right? One way would be that instead of having just 2 pairs of prover verifier, we would add a 3rd one, okay? In that case, there is a trick to make, so if you have a scheme that is secure against classically correlated provers, adding 1 makes it secure against quantum mechanically correlated provers. The reason we could not implement this is because the known bounds for these kind of schemes scale quite badly. And so instead of being able to do the experiment in 1 second, we would have needed 1 month, okay, which defeats the purpose, I think. Another idea is that you could complexify the graphs. Okay, so if you start from 1 graph and you have security against classically correlated observers, there is a way to generate a more complicated graph where you would then have security against quantum provers. But again, this is also impractical, and it's so on the quantitative side, it's not so clear how to do that. And there is another beautiful solution that was invented very recently, so by André Chailloux and Barsamian, which is just to rely on a different problem, right? Go away from 3 coloring. And so what they used is the problem of syndrome decoding, which has to do, so basically the idea is that you're given, in the challenge, you're given a big matrix and a vector, And as a solution, you should provide a vector that, when multiplied by the matrix, gives you the final vector, right? And I think maybe with a constraint on the Hamming weight of that vector. So this is one of these problems that is used in post-quantum cryptography. So it's nice because it's also a problem that is believed to be very helpful even for quantum computer and perhaps even on average instances of the problem, right? Now, there is a drawback for the scheme of Chailloux and Barsamian, is that it's a bit more heavy on the implementation side. In particular, the amount of information that must be communicated in every round is a couple of kilobytes, I think. Okay, it's not just 2 traits as we had. But I think that with our hardware, their protocol could be implemented maybe on a distance of 1 kilometer or something like this, which, you know, is still interesting. All right, so I guess I came to the end. I hope I convinced you that this is an interesting idea, even though it goes away from quantum. But okay, hopefully we can report further progress in the future. Let's see, perhaps on shorter distance implementation and ideally secure against you know, general attackers. Okay, and let me thank you for your attention and happy to take questions.
Oh, thank you, Nicolas, for the very nice and, you know, entertaining talk. It's very scientific as well as, you know, relatable as well. So yeah, I'll open to the floor. If you guys have any questions, please go ahead and you know, share it with Nicolas. If you don't want to verbally talk into your mic, you can also share your questions via the chat function, right? Okay, Nicola, I guess, you know, people are still very shy or they're so used to Zoom, right? I mean, one of the issues that we have faced when giving lectures is that the students, they don't reply, right? No matter how much probing you do. Yeah, okay, but I do have a few questions and hopefully we will warm up everybody. And yeah, Marco, you're in the same, you know, country now as Nicola. You should also, you know, pressurize him a bit, even though you are in Zurich. Okay, so yeah, I understand this whole idea of using relativistic constraint to remove the computational argument that one typically uses in the zero knowledge proofs, right? But do we really have to play with distances? You could maybe talk about isolation of devices, right? And then that will be a lot easier. You don't have to, you know, talk about using ASIC to try to bring down to 1 meter separation. Is that something that has been, you know, discussed or put forward by Hugo, for instance?
That's a good question. But okay, you see, it's a problem that we also face in QKD, right? So isolating devices is quite tricky.
Yeah, so, I mean, you're right? So about on device independent quantum crypto, right? Typically, we don't want to talk about the locality loophole, right? We would defer it to just isolation of devices, and you know, this is a lot easier to achieve in practice than to talk about physical separation. Yeah, so I'm just wondering, because if you're going to use this as a technology, right, then it would have made, like, you know, life easier for Hugo if we just isolate the devices, put it in some Faraday's cage or something like that, right? And yeah,
I agree. Well, I see still a difference, though. No, that for instance, if you do device independent randomness generation, right? Okay, so I guess people have different takes on it, but typically my take would be there that you want to be a bit careful about the implementation of the devices, right? There might be some technical noises inside these that you do not control, and you want to separate the true quantum randomness from this kind of noise, but you would not, you know, believe that or look at your devices as being malicious and trying to communicate between them. So in that case, I think it's fine, as you said, indeed, to relax the the locality conditions, right? But when you go to a scenario like this one here, or perhaps to the QKD, for instance, there it's more critical, I think. And so if it's possible to do it with a space-like separation, okay, at some extra efforts, that's true, but I think it's really worth it.
Okay, yeah.
But if you want, I will ask Hugo what he thinks about isolating devices out of curiosity.
Then Hugo might actually come to the conclusion that I'm becoming more experimental than I should be, right?
Definitely.
Yeah, if there's no follow-up questions from the audience, then I have another one as well. You speak about, having security against classically correlated provers. So do you have an idea, for instance, of an explicit attack that would make use of, let's say, entanglement to break the protocol?
No, at the moment, well, as I said, the point is we don't know, right? In fact, there are people like Claude who believe that it's secure, maybe at an extra little cost in soundness, or perhaps at no cost at all. But we have no proof, right? And that's the beautiful thing about the more recent paper of André Chailloux and his colleague, that, okay, they have a formal proof.
Mm-hmm. And do you have any intuition why adding a third pair of prover verifier would actually, imbue the entire protocol with quantum security? Because the initial intuition you gave, right, is like the prisoner dilemma solution, right? You want to separate the prisoners, but now by adding a third prisoner, why is it that you suddenly gain that quantum advantage?
Yeah, it's a good question. So Claude had explained it to me. I think it essentially relies on a trick that was invented in the context of Bell inequalities or non-local gains. And it's the idea that if you have a Bell inequality for two parties, right? And so a bound that holds for any classically correlated parties, then there is a way to construct a tripartite scheme where the classical bound will translate into a quantum one. That's the idea. But now on top of my head, I can't remember.
I think it's just monogamy of entanglement, right? Essentially that. Because
it must
if three parties, they essentially two of them can only be classically correlated. But I mean, in some,
might be constructed in some way like this, yeah. It might be that indeed you play some non-local game with either one pair of parties or another one alternatively, and so therefore, yes, using monogamy.
They cannot both be entangled,
Yeah. Mm-hmm. Or perhaps even monogamy of no signaling. I don't know, but yeah, something like this.
So have you thought about how one would practically do this? It's okay, abstractly you can talk about agents of the proven verifier, but if you want to use your ATM, how would you actually do this? So you have to come with your whole family and they go to different ATMs?
Oh, so with the ATM, it would be good to limit to 2 pairs of provers and verifier, I agree.
So both hands, if you can do it to 1 meter, maybe.
Yeah, if you can do with 1 meter, 50 centimeters, you can do a scheme with 2 cards. No, but maybe, what is more realistic is that there might be, situations, for instance, where, the authentication is very important because it's not only just about getting $20 from the ATM, right? So, for instance, when 2 companies are signing a deal or something like this, and so there you could imagine a scheme where imagine two large companies, right? They each have a building in two separated cities, right? 2 distant cities, and so therefore you could imagine that there they do this double terminal somehow identification.
Okay.
Something. But it's okay. It's a good question, because indeed, I think at the moment there is clearly, some sort of potential, right? Because authentication is such a universal problem. But it's clear that the killer application, we don't have it yet.
Yeah.
But we are looking. There are some ideas out there, so we'll see.
I think it's still fairly speculative at this point, right? I mean, the work is based on scientific merit rather than it's direct application at this point in time. And I'm pretty sure that Marco didn't want to share his ATM card with other people as well, right? 1 meter he can still do it, but 2 meters, right? He needs to get his son to stand on the other end of the terminal.
Yeah. No, I agree with you. That said, we got quite a lot of feedback actually from even companies that work also on blockchain related things, where their identification is a very big problem. So we'll see. But on the ATM side, as I said, I'm less optimistic.
Mm-hmm. Okay. Yeah, no problem. Any other questions from the crowd or Marco? If no more questions, then let us thank Nicolas again for his time, and for making the effort to give such a nice talk. Yeah.
Thanks.
Okay.
Thanks for the invitation.